Hey, what's going on, everybody? So today I have a special treat, and this is a code review. This code review covers all the code that's relevant for the Metamorphic Malware Detection using graph attention networks. That is the topic of my PhD thesis. So I thought as a first step, I would just go over a few of the model training scripts and notebooks that were involved when I was carrying out the experimentation. Perform the training, validation, and all the final tabulated work. So with that, I think it's worth going over at least some of the original benchmarking. So this would be benchmarking where we're testing on a torch geometric data set, but we're not using any of the malware data sets that were obtained. Then I'll leave that for a second video. Maybe it's worth mentioning that everything that's discussed here is in the Gap Malware GitHub repository. I think I make multiple references in the thesis document, but there's a bit of a setup. You can do so through an Anaconda environment. I think there's a few, maybe that's the only way I have it. And then just a citation usage here. So this is pretty old work when I originally created it, but all the code is found here. So maybe it's worth mentioning exactly what libraries we're starting off with. First, we make heavy use of torch geometric, and that's just basically for their GNN layers, GCN-conv and GAT-conv. That's intention, convolutional graph neural network. This is just a simple convolution layer. Data sets, we make use of a few of these data sets. Again, this is just for benchmarking. So these are graph benchmark data sets for the Planetoid and Facebook page. Planetoid is a group of data sets. A few transforms, and then I also make heavy use of sort of these lightning pipelines. They just make it very easier to track gradients, validations, schedulers, so on and so forth, right? So makes it much easier to log all of that information. So that's why I make use of this. Yeah. So there's a multiple import there. So pretty much starting off with the data module, which imports from the Lightning data module. That's the parent class. What we're trying to do here is pretty much just setting up the data module. What does that mean? Well, we have our simple setup. That's kind of the default for all these Lightning data modules, where we're performing most of the data loading in this setup function. So it's just checking if we're doing Facebook or the core SiteSeer data sets. And if so, we're saving that data set to disk. So a lot of this will save it to disk. A lot of this has to do with how we split the training, validation, and test sets. So we're saving into this data variable. A lot of this is just saving in some form of config, the number of classes and the input dimensions of these data sets. And then, as is typical with Lightning data loaders, you have to wrap it around this data loader kind of class here, where we pass in the data, our batch sizes, and a lot of information when it comes to actually the batch loading, right? And then for the validation loader, it's actually pretty much the exact same code as the train loader. We don't treat it any differently. And that's just because these actually save with training and validation masks, right? So whenever we want the training or validation set, we just have to apply the mask onto the graph class, which is how it's contained in torch geometric. So that's kind of why these are initialized as exactly the same. Going here, we get a little bit more. So now that we have the data set and we have this in this data object, and then we wrap it around these data loaders, ultimately in this benchmark data module, we go into creating this is pretty much the module, again, wrapping around Lightning module. So here we have a simple GAT, graph attention network classifier. And one of the things that's worth mentioning that's unique to this is that we are grabbing our complexity GNN layer, which I'm going to discuss in a bit. But for the time being, we're creating our classifier with a optimizer schedule and a learning rate. Maybe it's worth mentioning where this config comes from. Okay, I don't initialize it yet, but so the complexity GNN, we are loading it with a given config, and we're casting it to our GPU. So this complexity GNN is in models, definitions, layers. So actually, maybe I'll leave it out for the time being, just because I think that's probably a video in and of itself. But this GAT classifier, again, it's a wrapper around the complexity GNN layer. And then this is me just kind of hard coding some class imbalance, but ultimately we're doing a cross entropy loss just to account for any, because this is cross entropy loss can work with any sort of number of classes above 2. So cross entropy loss is the general version of it. Technically, you could just use a binary cross entropy, but cross entropy works with just two classes as well. And then we go and configure optimizers. So what does configure optimizers do for us? Well, it saves the atom state, or sorry, the stateful atom optimizer. And as for schedule, this is just to sort of know, let the training data loader know when it should stop. So we pass in the optimizer. We're waiting until validation loss stops decreasing. We factor about 20% factor by which the learning rate is reduced. Patience, number of epochs with no improvement. Lower bound of the learning rate, so it doesn't get much less than this. And then we show it all to the terminal with verbose equals true. And then we pass in what to monitor, which is the validation loss. So the validation loss, and we want to minimize it. And when we notice there's no change, well, then we change the learning rate. And then all this, we return the optimizer and the schedule. So that was configure optimizer. Going back up this, so now that we have all the state that we need for the optimizer and the scheduler, the important things that's kind of like a lot of the hidden in benefits of these Lightning modules is that we can create these class functions for the forward network, for the forward step, and for training, validation, and even a test set if we wanted to. As of right now, just for this work, we just have a training and validation step. So I'm going to get into that in a second. The first thing that happens, okay, I think we go into the training step. So whenever the Lightning, we tell the model that we're training, it's going to look for this training step function. First thing it's going to do is, based on this batch, we're going to extract the mask. And the reason why is because earlier on, when we said the training and the validation, we returned the data loaders and we didn't return a different one, is because in this data, we have data.trainMask and data.valMask, right? So it's actually the same object. So for these graphs, all we actually have to do is do .trainMask, and then we get a mask for exactly which training and validation nodes and edges correspond to the training versus the validation. Next thing we do is the feed forward and loss. So there's a lot of code that's actually hidden in here. Self.batch and self.criterion. So what self.batch will do is it's actually just going to call the forward method up here. First thing we want to do is take that batch, take the X, which is the nodes and the node features, cast it to GPU, cast the Y to the GPU. Then what we do is we actually take the edge indexes that are connecting these nodes in these benchmark data sets, cast that to GPU as well. And then we return self.module. So we return the net output, so the final output, and then the Ys. So I'm going to get into the model and all that in the next video, but just know that this is the feed forward method and that we're returning the net output and the labels. So when we do that, we have our logits and Y, and that's just logits because it could be multi-categorical classification. So those final outputs before you actually determine the loss are called the logits. When we have that, we have our self.criterion, I should say, which is just our cross entropy loss. So what is it doing? It's saying for these outputs, only look at the training ones, and for the Ys, only look at the training ones and determine the loss. With that, predictions and accuracy, we just take an argmax for the logits over the first dimension, and all this does is just looking at all the cross entropy loss, produce a probability distribution function over all the classes. So it takes the argmax, in which case it just sort of says, hey, the column, I think it's rows and columns, yeah. So the column, which has the highest probability in the cross entropy loss, mark that as a 1 and mark the other ones as 0. So the highest probability is always for the model what it thinks is the highest probability class. So it's predictions. And then the accuracies, we're doing something similar where we take the predictions. We say, are they equal to the masks? We have to dot item in order to take it out of the GPU. And then we just do a quick divisible by the length of the number of samples to get our accuracies. And one of the benefits of using Torch Lightning is that we can have this logging function that allows us to log our training loss and accuracy. So pass in loss and accuracies. And for each epoch, we're tracking that and then returning the loss. So this was this feed forward method. So this feed forward method, training step. Yeah, and then it returns our loss. Validation step is exact same thing. The only difference is we're dotting the validation mask to get the validation step. Everything else is exactly the same, except we're logging validation loss and accuracies. And then the mask that we're passing in is our validation mask. So all the code is exactly the same. The only difference is we're actually also performing the feed forward on the whole data set as well, right? And that's just, it's easier to do it this way. But the difference is, like I was saying, is the validation, this mask is now the validation mask. So it's only going to look at the nodes that are in the validation and the labels that are in the validation, and then compute loss just based on those. So all this is based on the mask, which is the validation masks. So now we kind of know how this classifier work. Again, we're not going to go into the model just yet. I'll leave that to next video. And then we pretty much finished up with this data loader. Now we get into a little bit about, now we're kind of starting lower end. We're getting more abstract in terms of the machine learning, deep learning pipeline and the flow of that. We use a library called Optuna. Optuna is pretty much just being able to, I guess, over a set of all the possible hyperparameters that you want to choose, it will actually test various different models and actually log best validation accuracy and even return the model that was determined to have the best validation accuracy, for example. So it's pretty much a way of testing various models over various hyperparameter sets. So this is all a function of the Optuna library, where we have this define objective function. And then even within Optuna, we use MLflow for all the tracking of gradients and then logging the models and naming. First thing we do is we set hyperparameters combined with model config. So what is this doing? This is setting all the potential hyperparameters that we potentially could use. How is it doing this? Well, learning rate is something that's a hyperparameter and it could vary depending on the model and the data set. So one thing we do is that we pass trial.suggest log uniform, and it's going to grab a learning rate between 1 to the -4 to 1 to the -1. And what it's going to do is it's going to randomly select one of those. Yes, so it's randomly going to select that on the log. So it's going to grab 1 to the e to the -3, 1 to the e to the -2. So that's the only possibilities. Alternatively, you can have something like, okay, well, this is maybe not needed because max epochs doesn't really matter because we have early stopping. But an alternative to log uniform is to suggest an integer. So we suggest an integer between 5 and 40, right? The min and the max. This is use fractal dimension. This is more so related to the fractal dimension implementation and whether or not we use it. So this is to test whether it's, we test models where we did use it and we didn't use it. So it's suggesting a categorical from this list of whether to choose it or not. Things like n-gram has to do with the data set, right? So if we're using 1, 2, or 3 n-grams, we tested all the models of n-gram of 1, 2, and 3. Norm, this is a function of the complexity layer. So it's grabbing one of these. This is for the order of the norm. And additionally, layer type, we want to quickly test graph attention versus just simple graph convolutional. So it's also going to grab that. A few other things worth mentioning. If we're using the fractal dimension, then there's a few other considerations that we were testing. Whether or not the complexity layer can exist early in the model, deep learning earlier in the deep learning model architecture or later on. So this actually has to do with placements of whether or not we put in the first layer, first and the second layer, or the second layer. And one additional thing for the complexity layer is the use of the radius of gyration fractal dimension, whether we used it or not. And if we're not using any of those things, well, we just set the parameters to none. Here is when we actually initiate the data module. So we did define this, and I did explain this earlier. We pass in for whatever config name that we want. We're going to grab that data module. We're going to call data module.setup, which takes care of all of this initialization for us, saves the model to disk. Where was I? Right here. Yep, just disks. And then we do one other thing. This is for the architecture of the model. So now that we know that we initialized a particular benchmark data set, well, we need to, for the architecture of the GNN, we need to know what the input dimensions are. So we grab that with data module.input dimensions. And additionally, we're also testing different model architectures in terms of the neurons for each stage. So H sub 1 or HL sub 1 refers to the first hidden layer, the second hidden layer, and we have a different number of neurons for each of those layers. And of course, depending on what benchmark data set you're using, you can have a different number of classes. Not all these are. The problem of malware versus benignware was a binary classification, but with some of these other benchmarks, I think some of them have a number of classes up to 8. So we also add that to our params. And then this is where we start to initialize the model. So config.update params. So we're passing in a config file, which I guess potentially I'll get into later, but maybe I'll do it right at the end of this video. But we're updating it with the params that we all initialized here, so it's just a single dictionary. So this is just updating a dictionary with another dictionary. And then we initialize our lightning GAT classifier with all our configs, and then we got a model. With regards to the lightning trainer, as part of the lightning module, you have this trainer where we track, again, we're just getting higher and higher up in data orchestration and abstraction, where we have this logger. We set it to true so that we can see the results. And I think it also saves it as a text file for what's going on. Checkpointing just has to do with if we have a model that we're training over time, every 100 epochs, for example, or when a certain validation accuracy or validation loss, when we obtain a certain one, it can actually save the model as a checkpoint. So that's what it's doing. This is very useful and is almost imperative for large models where you're training it over many GPUs, over many computational GPU hours. We want to constantly save our checkpoints of our model and those weights. So we don't do this just because everything runs pretty quickly. We check how many epochs it should run. We run it on GPU. We have a single GPU, and then we use our callbacks where we're monitoring the minimum of our validation loss. And that's how we know the model stops earlier. And then in the ML flow, we call the log parameters, and this just allows us to view all the config that we needed later on, and it tabulates it very nicely for us. And then finally, we take our trainer, we fit to our model, and we pass in our train and validation data modules. And then all we do is that we return the callback metrics validation accuracy. And the reason why you do this, from my understanding, is because this is still all under Optuna, subjective function here. From my understanding, Optuna needs to check for its best model, what is it looking at? And for this one, our model will have the best validation accuracy as our key indicator, right? So it's actually tracking validation accuracy to know which of these models of these randomly initialized parameters is the best model, and that's how it tracks it. All this here has to do with tracking the name of the experiment and categorizing it, so let's not worry too much about that. This again has a lot to do with ML flow being able to track it over a local server. How you name it, how you create the experiments, how you start to run it. You can nest it, and I believe that's because you can run multiple models at the same time in parallel over multiple GPUs. Could be wrong about that. Some leftover config for some things. And then this is how we actually create our Optuna study. So we wrap it around this ML flow start. Optuna will create the study in order to maximize, and then we optimize over 100 trials. So this is saying our objective function, number of trials, and timeout. So objective is everything that we define here. So I'm passing that into it. Number of trials will actually say how many times do I run through this and randomly initialize the parameters. So we're grabbing 100 different models that we're testing, and a timeout just in case there's some hanging or we want to stop it prematurely. This pretty much summarizes it. With MLflow and Optuna, we have this nice indication for whether or not we're actually using GPUs versus tensor processing units or any of the other ASIC devices. We have our models, and this is pretty much the number of parameters. So we have over 18,000 parameters in our complexity GNN. Summarizes it nicely for us, and we can see that it's ran for about 12 epochs. At 11, it had a certain accuracy, and then early stopping told it that it should stop at 12. Max epochs could have been something closer to 100, but with the early stopping, it'll stop prematurely when it notices that validation accuracy no longer decreasing. And then we see epoch 11 again, and I think this is just each different model. Remember, it's training 100 different models, and the number of layers and the configuration changes. So we can see that this particular model, it's had 18,000 parameters, but this next one initialized had only 8,000. And then in the config, in the MLflow dashboard, we can see exactly what the config was, and we can see that this particular model used the complexity GNN, it used GATConv, it did use list learning rates. All that is cached and saved for us in an MLflow dashboard. So running all these models, you can see you can run something like 100 models. Yeah, and some of these ran only for 8 epochs, 12 epochs, 33 epochs. Again, that's a function of all the different settings and the configurations that you chose for the model. So with that, I think this is a good way to stop. I think maybe it's worth going over that config, just because this is pretty much the standard for all the other notebooks and the models that are running. A lot of this is just basic configuration. So what does that mean? We use rich handler just for logging purposes. We have all of our base paths, where we create our model stores for our different models. Output directory, so we create these on the fly. For MLflow, it needs to know where it's tracking. So it's tracking. MLflow is going to look in the model registry in order to grab those models for you to view in the dashboard. This has to do with all the different ways that we are logging the output. So logs.path, basepath.logs. So I'm wondering if, yeah, so maybe this is it. I can't remember if there's different logs that are stored for different purposes, but yeah, I'll leave that alone for now. But what this, let's go back to it. Where was it again? Config.pal. So what this is doing is it's actually setting if we're looking, if particular, when we're debugging and when there's logging, if there's errors info, what kind of information are we grabbing? And you can see the errors are actually stored in error.log. The info is stored in info.log. And then for a lot of this stuff is actually outputted to the console. And a lot of this formatting here just has to do with, okay, what exactly things are we looking at? Well, we want to, if there's an error, we're capturing the line number, the function name. This is all just for debugging purposes. We're logging everything that's logging.info in terms of priority or above. A lot of this has to do with grabbing the logger and rich handler initialization. So with that, we've kind of gone over pretty much the data orchestration part and the data loading when it comes to the benchmark data sets. There's a lot more involved when we're actually looking at the malware data sets. So that'll be the topic of the next video. And thanks for watching, and leave all comments in the comment section below. Thanks.